momentum of the Lagrangian patch. And there's a strong relation, but overall there is some offset here, offset about 0.15 dex, which roughly corresponds to the scale you need. So indeed, the stars, even in the baryons that will in the end form stars, have lower angular momentum than the dark matter already in the initial conditions. So there's some kind of special selection. Maybe they're just coming from what will end up as the inner part of the halo. We'll see in a bit if that is actually true.
Earlier you said that within a sphere the angular momentum is 0.
Right.
But it's not any sphere, right? You can't just take an arbitrary spherical volume.
Yeah, so in the initial conditions it's actually in any sphere.
Any sphere. Okay.
Any
So
sphere.
now there's another radius here, and it's
Right, so this is in a final halo.
concentric within the...
Yeah, so in the final, in a nonlinear collapsed halo, you definitely can get net angular momentum within a sphere. The property that the angular momentum is 0 within a sphere is when you have a completely curl-free field, which is true under the assumption of the Zildovich approximation.
Now that's changed. So
right.
inside this sphere,
right.
You can have angular.
Yeah, because this sphere in the final state actually has material that came from a non-spherical region. So, and if we compare the angular momentum of what will end up as stars and what will end up in the dark matter halo, and we compare the angle between these two in the initial conditions, we also find that they're not completely aligned. There is a misalignment of 25 degrees there. So just to get an image of what this looks like, so this is in the initial conditions, a region, so essentially all the particles that will end up in a spherical halo. This is what it looks like for one example, again colored by angular momentum, and this is for exactly the same halo, but now just taking all the particles, or tracer particles if you want to get technical, that of baryons that will be locked inside stars in the final time. So you can clearly see there's some truth in saying that the stars come from the inner parts of the halo, but clearly this is not a spherically symmetric situation, and but certainly the stars do not sample fairly the region in the initial conditions from which the dark matter collapses.
Why is there a gap at the top then?
These are really pretty features. I think maybe they have to do with mergers. So somehow when you have maybe shells forming after mergers, is somehow related to these shells in the initial conditions, but actually I don't have a great answer for this. I think it would be interesting to understand better, but it's a recurring feature. Okay, and just want to mention briefly a couple of papers from recent years that also noticed a significant difference between the Lagrangian patches of dark matter and baryons. So papers that showed essentially how far particles go from the initial conditions to the final time, and showing that gas particles go much further over cosmic history than dark matter particles. And also another paper that showed that only 75% of the mass in the final halo comes from kind of the overlap region in the initial conditions where both dark matter and baryons came from the same region. So 25% of the mass in the halo came from a region where it's only baryons or only dark matter ended up in the final halo. And there is a relation between this overlap fraction and the final alignment between the two components. Okay, so this was some important distinctions about already just in the linear phase between the angular momentum of dark matter and baryons. So let's move on to say a few things about the quasi-linear phase. So when I say that, I mean kind of around the turnaround time. So before the final collapse of the halo, but when the perturbations are non-linear anymore. A paper from a few years ago made quite a strong claim that contradicts the regular assumptions that we've discussed. By looking at simply the angular momentum profile as a function of radius in halos and comparing the angular momentum of gas and of dark matter around or just outside the Vera radius, so in this range. And they've shown that the gas systematically have up to a factor of 2 larger angular momentum just around, in a shell around the virial radius than dark matter has. So they use this to say, okay, maybe gas is actually accreted onto halos with twice as much angular momentum as dark matter, which would change significantly the amount of angular momentum available for stars to form out. And they trace that back to a difference in the moment of inertia. So here's just a picture of, with the virial radius here, of some halo, where cold gas is shown here to be distributed in these thin streams, versus the dark matter distributed in much thicker streams. And hot gas actually distributed even having an even lower moment of inertia. And so they argued that the larger moment of inertia due to this thinness of these streams of gas versus dark matter accounts for higher angular momentum at accretion. One problem with this inference is that we don't know for sure. If you just look at this shell around the virial radius, you don't know for sure that what's there is necessarily being accreted. There's a lot of mass there that could have been already spent some time in the halo and thrown up. So, and another issue with making a strong inference from these studies that we don't necessarily know that this cold gas is actually going to be the stuff that stars are eventually going to be made out of. So we went back to this and looked at the illustrious TNG simulation and measured directly using these tracer particles, essentially so looking again at the stars and at the dark matter in the final time, and following them backwards in time, the same mass, and asking it each time that subset of the mass that is accreted at any certain time, what is the relation between the angular momentum of the gases and the dark matter? And what we find is that essentially they lie right on top of each other. Okay, so this now as opposed to that, if we look at the mass, the stuff that is inside the halo already, we see that the gas in green here has indeed about 50% larger angular momentum than the dark matter in gray. This is for things that are inside the halo. So this is caused by nonlinear processes occurring within the halo. For example, torques due to dynamical friction between dark matter and gas that can transfer angular momentum from dark matter to gas. But at the time of accretion, we find that they have exactly the same angular momentum. Another interesting point about the quasi-linear phase is from a paper a few years ago that found that these galaxies tend to form in regions where the large-scale structure is well aligned with itself as a function of radius. So what's shown here, for example, are 2 galaxies. This will form into this galaxy, and this region will form into an elliptical galaxy. They're shown at the turnaround time. And these arrows here show the measurements of the angular momentum direction in different shells. And we see that this galaxy, the angular momentum is aligned in different shells around the forming galaxy, while this elliptical galaxy, every shell we look at has a different orientation of its angular momentum. And this has been generalized, so this is essentially the profile as a function of radius within the angle of each shell with respect to the overall angular momentum of the halo. And we see that for these galaxies, these profiles are much closer to a cosine of 1, but for elliptical galaxies, they're much lower. So these galaxies tend to form in these coherent large-scale regions. Interestingly, we don't find the same thing when we look at the TNG simulation and at the coherence of the initial conditions. So again, we do a similar separation by galaxy morphology or angular momentum, and we see that all halos, all proto-halos in the initial conditions have exactly the same self-misalignment as a function of radius. So I think this still is an open point. It could be that these different simulations actually behave differently, or it could be that there is something that's happening between the linear phase and the quasi-linear phase that brings about this correlation. Okay, so we're done with the linear and quasi-linear phases. talk about the nonlinear phase, where the standard picture assumes a conservation of the angular momentum of the baryons that they obtained in the previous phases as they collapse, cool down to the center of the halo to form a galaxy. So let's explore that. To do that, we again use the similar technique. We take all the stars in the galaxy at redshift 0 and we follow them backwards in time. And through the various processes that occur in this nonlinear phase. So here is this popular picture of the circumgalactic medium, where we have the disk galaxy, we have accreting gas coming from outside, and we have winds blowing out gas from the galaxy that may be then sometimes recycled back into the galaxy. This is a picture I made of the same thing, where we can follow individual mass parcels, tracer particles, as they accrete onto the halo, cross the virial radius, fall onto the galaxy, kicked out of the galaxy. They can be kicked out and fall back several times in what we call the baryon cycle. In the end, they arrive to the galaxy one last time, going around the galaxy as gas, forming stars, and then getting in the end to redshift 0. So what we're doing in the next few slides is just compare the angular momentum of these different events in the history of this, if you want, a proton as it's being accreted.
By the way, the center of the galaxy moves all the time.
Right, so this is always relative to the center.
Right, but like if there is a merger, then it moves somewhere else.
Yeah, right. So there is some noise introduced by that. Yeah. But what we will be contrasting is simulation like Illustris, or specifically